The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Welcome to today's webinar. My name is Jeremy Henick. I also have Joe Belland on the line from Isograph. Joe heads up our technical support and training for North America. Today we'll be talking about how to use a Markov model as part of a fault tree analysis or reliability block diagram. The Markov is a very important piece to these modeling tools in that it helps you properly model the behavior of your system. But I'm not going to get into that too much. I'm going to let Joe take care of that. Just a couple things before we get started. This is a very important point. We've had a few webinars leading up to this, and the Markov software is included with your Fault Tree Plus software or your RBD software. A few weeks ago, we had a webinar on event tree analysis, and there was some confusion, I guess, on whether or not the software is included with your Fault Tree Plus or a reliability block diagram software. And Markov is included with both Fault Tree Plus and RBD. This is part of a webinar series. You can see I've checked off several because those are webinars we've already done leading up to this.
Jeremy, can you share your screen, please?
Oh, can you not see it?
No.
Oh, sorry. All right, my bad. So to start again, this is part of a webinar series we're doing on our reliability workbench software. So leading up to this, we've done a web meeting on Fault Tree, the 61508 and how you use it in Fault Tree Plus. The data links, which is mostly moving from Famica to Fault Tree Plus, but we did deal a little bit with RBD to Fault Tree. A couple weeks ago, we did event tree analysis as part of a Fault Tree Plus study where you can link the data between the two. And then today we'll be doing a web meeting on how to use a Markov model in Fault Tree Plus or the RBD software. If you did not attend any of the previous webinars and you'd like to see them, please just send me an email and I can send you links to the recordings. Just one more bit of information. You'll see on your screen there's this pop-out for the GoToWebinar software. You can minimize it by clicking on the small arrow up at the top. You've probably noticed everybody's muted, so if you have any questions, please click on the questions dialog. It'll open a pop-up and post your questions to that section, and then Joe will stop periodically to answer questions during the webinar. Joe, unless I've missed something, why don't you go ahead and take over? I'll pass it over to you. Do you have control, Joe? Oh, there we go.
Hold on just a second. I think you made me the
organizer.
Yeah.
It's okay. You should.
Yeah, no, I got the I got the screen controls now. Okay.
Okay.
Which monitor do I want? I think I want this one here. Okay, so you should be able to see, it'll probably load in a second, a schematic on my screen for a processing plant. Let me just explain quickly how this works. We've had in the past webinars on building a fault tree from a schematic. So if you watched or attended that webinar, then you might be familiar with the general process of turning a schematic like this into a fault tree. So that's what we've done here for this particular schematic. This is from a processing plant, like a refinery. Basically, the way this works is that we have 3 input pumps, which pump our material that we're processing, that we're refining, through a furnace into our vessel, our reactor vessel. The mixture is heated in the reactor vessel, where it's separated. The gas separates and is collected and pumped via a compressor into a storage tank. The liquid product is also collected and pumped via a fluid pump into, again, more storage tanks. And we also have a backup, a relief system. In the event that there's a failure in the fluid pump, we can relieve the pressure vessel via our 2 relief pumps and a relief valve. Provision for these is to avoid an overfill or of the reactor vessel, so that we don't accidentally blow it up by having too much in it, too much pressure, or too much fluid in it. So it's just an emergency safety system. The buffers, these are called buffer blocks, but we're just modeling them in our fault tree as just storage tanks. The purpose of them is that in the event something fails up here, like the pump here fails or our input pump fails here, we can continue to operate the downstream equipment by drawing from the storage tank. So we have a little bit of time to repair it before we have experience a system outage or a loss of output from the system. So that's the schematic we want to model. So I've built a fault tree here. I'm not going to go take you through building the fault tree. We already did that in another webinar. We've built a fault tree here to model that system. So we have our 3 input pumps, the furnace and the reactor vessel, and then our output, which consists of the gas output, compressor in the backup tank, the fluid output, which is the fluid pump in its tank, and the relief system, which consists of the relief pumps and the relief valves, pressure relief valve. Okay, so we modeled all that. For failure rates, I just took some information from the NPRD library. Maybe, Jeremy, maybe we should have a webinar if we haven't already, talking about the library facility. But I've just pulled some information out of the NPRD library to get some failure data for these components, run the analysis, and got a unavailability for our top of it, the loss of throughput in our process plant. Okay. So that's simple enough, straightforward enough. We've already covered that in other webinars. However, now this system has a little bit of a twist to it. You might be able to see it in the schematic here. I put the schematic here. It's kind of hard to see. But so let me open up the main one. You'll notice under these pumps here, it says 3 by 50%. So we have these 3 input pumps. Each one can deliver 50% of the necessary capacity. Well, so you add those all up, and you get 150%. So basically, the pumps can overproduce. What that means, basically, is that one of these pumps can be a standby pump. We don't need to operate it constantly. We can operate off just 2 pumps, and let the third be in standby until it's needed, until one of the first 2 fails. Let it be in standby. Now that introduces a little bit of a tricky modeling scenario. What we call a strong dependency, where we have a standby arrangement. In fault trees, the events are generally considered independently of each other. That means when one basic event is unavailable, that has really no bearing on the unavailability or the behavior of the other basic events. If you've taken our training course, or if you're familiar with the fault tree methodologies, you might remember cover this in the training course, the multiplication law of probability, and that's one of the things used in calculating a fault tree. And multiplication law of probability only applies. It's an important tool in solving a fault tree, but it only applies for independent events. So the general assumption of a fault tree is that each basic event is independent of all the others. Now there's a few ways of getting around that. For example, common cause failure models. You might be familiar with using those. We can apply common cause failure models. That's one way of taking into account inter-dependencies. But the sort of interdependency between these pumps that we're talking about in this scenario, we're not really covered by common cause failures. What I mean by interdependency is, say pump 3 is our standby pump. What I'm saying is that the unavailability, or rather the failure rate of pump 3 changes depending on whether pump 1 or pump 2 is operating or failed. Now, in a fault tree, there's no real way of saying that. I can't say change this failure rate depending on this. The way, the mathematics in the background, the way it's working is it's just calculating a straight-up unavailability for each one of these independently, then multiplying their independent probabilities to get the probability. But that's really what our situation involves, where we have a standby pump. So sometimes we might encounter a situation like this when modeling a system, where you have some sort of interdependency between components that can't really be easily or accurately modeled in an analytical technique like a fault tree or an RBD. Of course, this all applies to RBDs as well, since it's the same calculation methods. So I might ask, well, how are we going to tackle this problem? Well, Markov is one of the tools that we have in our tool belt, in the workbench, so to speak, to be able to model these systems. Now, as Jeremy has mentioned in the webinar invite, things like that, the Markov is usually only suitable for these smaller systems. I wouldn't want to build this whole plant in Markov because it would get too large and too complex very quickly. But it's great for modeling just these smaller subsections, just these this one part of the system. So let's take a look at how we would build a Markov model to model just this section. So I'm going to jump down to the Markov section, and I'm going to quickly build through it. I'll give a little bit of a little bit of an explanation first of what Markov is. Markov we refer to as a state transition diagram. The Markov model consists of a series of states. Each state represents a possible configuration of the system, a discrete configuration, meaning that each one is separate from each other, and taken together, all the states represent every possible configuration of the system. By configuration, I mean something like operating or failed or whatever possible state the system could exist in. It's a state transition diagram, so we draw those states and the transitions. How often does one operating state give way to another? Now, just explaining that might make it a little unclear what I'm talking about. It might be hard to visualize. If you're a visual learner, it'll be easier to understand it as I build it. So I'm going to build my Markov model to model that 3-pump standby system. So I'll go through it pretty quickly. I'm not going to show or explain every single little option I'm clicking on. I'll try and give you sort of an overview of how it's built. So this will represent our 3-pump standby. So it's first, I'm just adding the Markov model. That's kind of like adding the top gate in fault tree or adding a new RBD system in an RBD. Once I've added my Markov model, I can now start drawing my state transition diagram with toolbar buttons on my main toolbar for doing that. First thing I want to do is add the states. I'll sort of explain this as I'm going along. I have different states for the different configurations. I know what I'm doing. You probably don't know what I'm doing yet. So it'll make more sense as I start to build it, start to name the states. So to add the states, I just click the add state and just drop the states into the diagram where I want them. And once I've dropped them in, I can move them around. If you have an OCD streak like me, you're going to want to make sure they line up perfectly with each other. Make it nice and neat and orderly. That looks good. Now to explain what each of these states mean, I'm going to edit each one in turn and add a description. So this first state, this represents the system configuration where basically everything's normal, everything's working fine. But 2 of our pumps are working, and 1 of the pumps is in standby. This state will represent where 1 of the pumps has failed. So from this state, what can happen is 1 of the pumps can fail. 1 of our operating pumps would fail. So we'd have 2 working, and the standby pump would come online to fill that gap. So 2 are working, and now 1 has failed. We're repairing it. The next thing that can happen, well, either we'll repair it, we'll go back and standby, or the other thing that can happen is while that 1 is being repaired, 1 of the operating pumps fails. We'll go to 1 working, and now 2 have failed. We'll have to repair those. And if before we can repair that 1 or before we can repair either of those 2 that have failed, if the last one that's working fails, we'll go over here where all 3 are failed. And I'll check this as an unavailability state. That means the system is unavailable when we're in this state. This state down here, this represents where the standby component has failed. So in this one, 2 are working, but 1 has failed and it's in standby. We don't know about it. That's where the standby component has failed. Okay, so that represents all the different system configurations, and if you're wondering why I've drawn them in this particular positions, why I've placed them there, well, there's a method to my madness. It sort of it'll make the connections make a little more logical sense. So now that I've defined my states, I need to draw the connections. I have toolbar bars, or toolbar buttons for drawing those connections. So I'll use the clockwise transitions. So what can happen basically from here, they can transition to here when one of the components fails. We can transition again if another one fails, and again if the third one fails. Repairing just goes the opposite direction. As we repair them, we work our way back up. So to draw the transitions, it's pretty simple. I just click on one state and then click on the next state and it draws the transition. To get this one into place, what can happen here, I'll use straight transitions for this. If the standby component fails, we'll go down to here. The two are working and one's failed in standby. And if one of the operating pumps still fails here, we'll go up to here. One is working and two have failed. So it's kind of a short circuit of this state here, depending on which fails first, when the operating pumps or the failed pumps. So that that defines our diagram. The next thing we want to do is add transition rates, basically the failure and repair rates. The transition rates basically tell how often does one state give way to the next. So to do that is simple enough. I can just double click on it. Before I do that though, I want to jump back to my fault tree. I need to make a note of the failure rates that I'm using for my pump. So my failure rates, write this down because I'm not going to remember this. Put it in, copy and paste that in the notepad. I'll move that over to my other screen. Sorry if you can't see it. Just move it from my own memory. My failure rate and my repair rate. So that just so I can remember it as I put it into Markov. Okay, so let me define those transitions. Now the simplest way to do this is with transition parameters. Think of this like as a generic failure model in a fault tree. So on the parameter property, this is kind of like defining a generic parameter in a fault tree. So I can define the transition rate and name it. If you've ever gone to Markov and you get to the short description, you're thinking of that as the ID field, so you'll start typing it in and you'll notice it looks really weird. The reason for that is because the short description field is using the Greek symbol font. So whenever I enter a character, it appears in the Greek alphabet equivalent. So if I enter a L, that gives me a lowercase lambda. So I'll get that. So I can type in my failure rate, and I copied this as 1.73792 times 10 to the negative 4. Okay. Apply that. One more thing is I'm going to add a parameter multiplier of 2 because there are 2 operating components, either of which can fail. So the transition from 2 working to one of those being failed is twice the failure rate of a single component. Those are 2 components. So I'll do that, and I can continue to add those now basically by selecting it from the drop-down. 2 failed. In this state, there's only 1 operating, so the parameter multiplier will do 1 for this transition here. And now I need to add the repair rate, going back the opposite direction. So I'll add a new transition for that. I'll enter a lowercase m for the short description. Give me mu, and then this will be our repair rate. And the repair rate was 0.01 repairs per hour, about 100 hours to repair. And again, if we have 3 failed, we have 3 repair crews, so we can be repairing them all simultaneously. So I can enter that in. 2 are failed, and then here 1 has failed. One last thing, and then we'll take some questions, is the failure rate for the standby component. Now here's where it makes a difference. In fault tree, it would model all 3 pumps the same failure rate regardless of what's going on. With the Markov, we can tell it that the failure rate for the standby component differs from the operating failure rate. So I can either define a new transition rate for the standby failure rate, or I can use the parameter multiplier. Let's say the standby failure rate is only 50% of the operating failure rate. I can use the parameter multiplier for that. To say this is only 50%. Basically, the failure rate is halved when the component is in standby. We'll define this one here. Since 2 are working, we can have 2 failed, so it's twice the failure rate of 1. Okay, so I've defined my Markov model. Before I run it, I'll take some questions. Jeremy, is there any questions that you need me to address?
Yeah, there's quite a few questions here.
Sure.
So first question is there an absorbing state in the model?
In this particular model, there isn't an absorption state because the system is repairable. Absorption states refer to states with no transitions leading away from them, and you can model that in Markov. You just draw a state and have drawn no transitions going away from it. That would be an absorption state. So you can do that, but this particular case, we don't have that.
Do you need to include a transition to complete a failed state to a working state?
I think that has to do with the absorption. Do you have to draw a transition from failed to working? If you don't, the failed state would be an absorption state, and you see that a lot in, or you see that most commonly in non-repairable systems. And again, yeah, so you can do that. This model just doesn't demonstrate that.
Okay, I think that's good for now. Okay. Any questions that I don't bring up, I'll be answering online.
Okay, so we've defined our Markov model. We can run the analysis by clicking the green traffic light. Let me check how I've set my options. Just want to check them over real quick. Make sure I set it correctly. I can run the analysis. And the way reliability workbench solves this is basically solving differential equations. Markov is one of the most mathematically complex calculations you have. It's solving differential equations for the probabilities of being in each state. Our probability of being in an unavailability state is really what we're most interested in. So the probability of being in the failed state. That gives us our lifetime unavailability. And we also have a mean unavailability as well, the lifetime unavailability. And then it gives us the results, various other results, unreliabilities, failure repair frequencies, and intensities, number of expected failures, etc. So, but in this particular case, what we're really after is the unavailability, or rather the mean unavailability over the lifetime, 2.2 times 10 to the negative fifth. Now we can compare that to our fault tree for the 3-pump system. We had 4.985, 10 to the negative 6 in this particular case, where in the Markov, it's a little bit higher, you'll see. You might be wondering, why is it higher? Shouldn't it be lower? Because we actually have a lower failure rate because the standby component, right, can fail at a lower rate. The reason why I think it ends up being a little higher is because there's when the standby component fails, we don't know about it. So if our backup fails, it will remain in the failed state. So you can see the average unavailability or average probability for being in this state is quite high. There's a good chance that the backup component will fail and nothing will happen. So it sort of negates some of the redundancy we get from that component. Let's make this Markov model a little more complex to, again, model how this would probably actually work in real life. Now, that standby component, I mentioned that if it fails, we don't know about it. Well, in reality, we're probably not just going to let it sit. We're going to probably check it periodically to make sure it's still operating, right? So if it does fail, we do want to know about it. We won't know about it immediately, but we can check it out periodically, start it up every once in a while to see if it's still working. So to model that in a Markov model, we'll use phases. Phases in Markov allow you to redefine the transitions for each phase. So you can say that during different phases, we have different transitions or different transition rates. So let me start defining some phases for this model. So I'll click the Add Phase button, and I'll define 2 phases in our Markov model. Phase 1 will be just the normal operation, normal operating. So I'll just call this operation. And what it wants to know here is the duration. How long does this phase last? And this phase will represent the time between inspections. So let's say we inspect every 6 months. So I'll put 4380 as our duration. 4380 hours is 6 months, or half a year. Now the other phase will represent the inspection. Now this will be what's called a discrete transition phase. Discrete transition phase have no duration. It's an instant in time during which there's a certain % chance of taking a transition. So during our inspection, we can say that there's a certain % chance that if there's a failure, we'll detect it and repair it. So I'll create that inspection phase. Now to define the transitions for the different phases, we have a phase selector drop down right up here on my toolbar. Right now we're looking at the transitions for the operational phase. I choose the inspection phase, all my transitions go away so I can redefine them. Basically we only have one transition here. If the standby component has failed, the point of this inspection is to detect that failure and begin the repair process. So if we do detect it, we move up to this state where the 2 working are now one has failed and the failure is known. That's what's unfortunate about this state. We can define a transition probability during a discrete transition phase, basically the probability that this phase will be taken. The default would be a probability of 1 or 100%. But here's where an interesting thing that we can do with Markov. We can model imperfect proof testing. If you're using the dormant model in a fault tree, the dormant model assumes perfect proof testing, meaning every failure is detected and repaired by the inspection. Markov, by using this probability, the transition probability, we can enter imperfect proof testing. So let's say there's only a 90% chance that if the standby component is failed, our test will detect that. It will detect only certain failure modes of the pump in standby. For instance, it will detect whether or not it will start up, or whether or not it can start up. It won't detect whether or not the automatic switching mechanisms will operate. It won't detect whether or not it will start up at full power and can handle a full load or anything like that. It's just whether or not it turns on and off. Okay. So then if that transition is taken, the phases would immediately switch back to the operational phase and we can begin the repair process. Now let's rerun the analysis. And we'll get a new lifetime unavailability, 2E-5 versus what was it before? Actually, what we really want to look at is the mean unavailability. I think it was 2.2E-5 before, so now it's 1.5E-5. Just a little bit lower, but we're a little bit better off. Okay. So we've created that. Actually, before I add this to our fault tree model, I should ask, are there any questions on phasing? Or really on anything else so far?
There's a couple questions that came up. In the calculations, you're using 3 mu. Someone's asking if you could explain that.
Oh, the 3 mu for the repaired transition here. I assume that's what you're referring to. So there are 3 components failed. The failure rate the repair rate for a single component is 0.01 repairs per hour, or basically 100 hours to repair. Since all 3 are failed, I have 3 repair crews. So the repair rate is 3 times the repair rate of a single component. Basically, one of them may be repaired first before all the others. So it's basically there's 3 that are can be undergoing repair. So the repair rate for the 3 of them is 3 times the repair rate for a single one of them. That's just how it happens to work out.
Okay, so that's why you'd use 3 mu instead of 1.
Yeah, Yeah, it's basically how many are being repaired at once. Because the repair rate represents, the mu represents the repair rate for a single component. Think of it this way, if when we get into this state where two have failed, we've already started the repair process on two of them, right? So if the third one fails, two of them might already be like halfway or somewhat repaired. So the repair rate here we shouldn't reset that to the beginning. So that 3 mu is basically how we take that into account. It's kind of hard to wrap your brain around it at first, but it just works out as you build Markov models and you compare it to a fault tree. You'll see that just kind of works out.
Okay. Last question is, do you need to connect all the states, like the inspection phase isn't connected?
Right. Yeah. So. Yeah, some of the states don't have any transitions in them in the inspection phase, and that's fine. The reason for that is because during the inspection, the only thing that can happen during that phase is if the standby component has failed, we detect it and repair it. That's all that can ever happen then.
Okay, thanks, Joe.
Okay. Now, so we've defined this Markov model, and what we want to do is, okay, this is great. This gives us an unavailability for the three-pump system, but presumably we don't want to stop here. Remember, this was all part of a larger fault tree, right? So we want to include that in our fault tree, because what we're after is this number up here, the plant's unavailability. So how do we include that Markov in the fault tree? Well, the Markov model basically works like a generic failure model. You can apply it to a basic event just like you could a failure model. So what we'll do is, instead of having a three-pump system with a gate and 3 basic events leading into it, we can basically model that entire system with a single basic event using the Markov model as its failure model. So let me do that. To do that, I'm just going to actually make a copy of this system. So I'll select my top gate, copy, select my fault tree pages node, and use paste special because I want to make a duplicate of it, so I can edit it. Okay, so now I have a backup copy. So now I actually have 2 different copies of it. And in this second copy, let me rename this plants with Markov. I can replace that pump system. Delete that. Actually, I know what I'm going to do. I'm going to be a little clever about this. I'm going to delete this, the 3 inputs, and then use the gate to event conversion to turn that into a basic event. And now I'm going to apply the Markov model to this event as if it was a failure model. I can do that simply by dragging and dropping it onto it. Now when fault tree runs the analysis on the system, it will use the Markov model calculated unavailability as that basic event's unavailability. Okay, so then I can click the perform analysis option and get a new top gate unavailability. So I can compare it to the original. Here's the original 5.115 E-6. Compare it to, with our Markov, 1.519 E-5. So you can see how more correctly modeling that pump system can have an effect on our top gate result. Any questions?
Yeah, would the Markov model provide similar results to the standby model in fault tree?
Someone knows about the standby model. Yes, actually the standby model is using Markov analysis. So this particular system I could actually almost do with the standby model. Let me just show the standby model. Basically that type of system, where you have a standby component with a different operating failure rate, that comes up a fair amount of time. So rather than forcing you to create a Markov model to model that, we actually added a standby model some years ago in the fault tree plus. Basically, it allows you to specify a failure rate and a standby failure rate, and however many components you have. So I could have just done it this way: 0, 0, 0, 1, 7, 3, 7, 9, 2, and whatever my standby failure rate was half of that, so 0.000. I'll need a calculator for this. I'll just abbreviate. Half of 17 would be 5, 3, 5, or something like that. Thereabouts. Enter my repair rate. I have 3 components, 2 operating components. Actually, I should say there's 2 operating components and 3 repair crews available. So I can almost do it this way. This would get me pretty close. The differences between this and my Markov model is for the operating components. That's the number required to be operating. I don't think this will capture that I can operate with just 1 pump. This would be like a voting arrangement, 2 out of 3 required voting arrangement. This also doesn't count, or doesn't get the inspections on my standby components. This models that I think standby failures are immediately repaired. This isn't taking into account that standby failures will go unnoticed until an inspection. But yeah, so this is this model is actually, if you do choose the standby failure model, it's actually using the Markov model in the background. Okay. Any other questions?
No, nothing right now.
Okay. Okay, well, that's about all I had, Jeremy. I mean, unless there's anything else that you wanted me to demonstrate.
How are the phases in Markov different than the phases in fault tree?
Right, so phases in fault tree apply specifically to the rate and fixed phased failure models, where you can define different phases, up to 10 phases, and a duration for each, and then set that the failure rate is different during each phase. So if I add a rate phased model, I can specify a different failure rate for each of the 10 different phases. You know, specify an overall, or different failure rates for each of the 10 phases. The way that they're different is basically that they're tracked completely differently. They can be used for similar purposes. In a Markov, you might use phases to define that transitions have different rates during different phases. That would be similar to using the rate-phased model. But they're not linked to each other, so you can create different phases for the fault tree than you can for the Markov. The Markov phases allow you to redefine transitions during each phase. The phases in fault tree, phased models, allow you to specify that the failure rate is different during the phases.
Okay, thank you. And Joe, just to confirm, these Markov models can be applied to RBD as well as fault trees?
Correct, and it's done in exactly the same way. It's if I jump over to RBD, you'll notice that my Markov model appears in the RBD project tree control, as do all my generic failure models, because that data is actually shared between the fault tree and the RBD. They're using the same failure data there. So if I create a new RBD and add a new block, I can just simply drag and drop the Markov model onto the block. And you can see the failure model is the attached Markov model.
Okay, thanks, Joe.
Okay, you're welcome.
Let's see. Well, that about sums up today's webinar. Let me just take controls here. Oops. Thank you for attending our webinar today on the Markov software. If any of you have any questions or, sorry, I got to the wrong slide, or have requests for future topics, we can always take a look at those. But you should have my contact information since you received the webinar invite from me. But please feel free to contact me if you have any questions. Thank you for attending today's webinar. Thanks. Thanks, Joe.
Thank you.